Good morning to all. Hope you are keeping well. Welcome to chemistry class. So in our last class, we have discussed about Gibbs-Helmonds equation, which is a very important equation. So delta G is equals to delta H minus T delta S. So delta G is nothing but Gibbs free energy change, enthalpy change, temperature, and delta S is the entropy change. So why we have introduced Gibbs free energy is, so in the second law of thermodynamics, so delta S is related to spontaneity. If delta S total is greater than 0, then the reaction is spontaneous. But the formula delta S is equals to, we have seen delta S is equals to, delta S universe or delta S total is equals to delta S system plus delta S surrounding. So surrounding was very large and it is very vast. To consider surrounding, it was difficult. So that's why we have introduced a new thermodynamic function, and that was delta G. And now we are using that delta G, and how we are going to remove this. So surrounding we shall see now. Clear? So now the criteria of spontaneity in terms of delta G or in terms of Gibbs free energy we are discussing. So let us consider a process being carried out at constant temperature and constant pressure. Suppose the heat equal to Q. So suppose let us think that Q amount of heat is lost by the system and it is moved towards the surrounding. System is losing Q amount of heat and the surrounding is gaining Q amount of heat. So let us mark that one. So we have an system here. We have a system and the system is giving out a Q amount of heat. So in terms of system, it is minus Q because it is losing. In terms of surrounding, it is plus Q. Clear? I hope it is clear. So now, so when you consider the system, so it is, so when you consider in that form, it is like that. So system is losing heat means it becomes minus Q for system, and surrounding is gaining heat means it becomes plus Q. But what we have considered the condition here, we have taken a condition is different. So the surrounding is losing heat and the system is gaining heat. Clear? So it is the whatever the condition we have taken, that is the opposite of the earlier one what we have discussed. Suppose a heat equal to Q is lost by the surrounding and gained by the system. So system is gaining heat now. System is gaining heat. So when system is gaining heat, so heat for system becomes plus Q and heat for the surrounding becomes minus Q because the surrounding is losing heat. Clear it is? So when we have written here the formula, let us check the formula. Delta S we have delta S is equals to delta S surrounding is equals to minus Q by T. Why minus? Because heat is lost by the surrounding. So system is gaining heat, surrounding is losing. So that's why it is minus Q by T. And we have one more thing. So we have seen already, that is in the beginning only we have seen, heat at constant pressure is equals to delta H of the system. Heat at constant pressure is equals to delta H for the system. So we have considered it as constant pressure. The process is carried out at constant pressure. So heat at constant pressure we can consider, and that can be written as delta H. So we can write, so delta S total is equals to delta S system. So we are substituting for this formula. So delta S system minus delta H system by T. So delta H system, why minus? Because it is surrounding is losing heat, and that heat at constant pressure we have written as delta H. Delta H surrounding is being written as minus delta H system by T. Clear? Now delta S total we have shifted, we have converted that one as system itself. Now So now in the next step, so multiplying the whole equation throughout by T temperature. So if you multiply there, it becomes T delta S total is equals to T delta S system minus delta H system. So we shall move to the next step, that is T delta S total is equals to same thing what I said, T delta S system minus delta H system. Clear it is? So it is system together. It is togetherly. It is system here. I hope it is clear. So we'll continue with the next part. So if at all, if it is done, then so we are going to rearrange that one. So delta H system we have taken, we have shifted slight arrangement we have done. So minus T delta S total is equals to delta H system minus T delta S system. So delta H system minus T delta S system can be written as delta G. So that is our what it is? It is our Gibbs free energy equation. Delta G is equals to delta H minus T delta S. Gibbs free energy, Gibbs Helmonds equation is delta G is equals to delta H minus T delta S. So delta H minus T delta S can be written as delta G. So we'll write it that one. So delta G of the system is equals to minus T delta S total. Clear it is? So it is negative sign. So delta S total it is, we don't have system or we don't have surrounding all together. So we are considering as total we are using. I hope it is clear now. So the spontaneity, now we can say that, so if at all, if delta S is positive, we know that, so for any reaction to be spontaneous, delta S should be positive. If delta S is positive, then only the process is called as a spontaneous process. I hope it is clear. This condition already from the second law we have discussed. If reaction has to be spontaneous, then delta S has to be positive. If you take a delta S is positive, so if it is positive, then whole of this term becomes negative. Then that means that, so if the reaction has to be spontaneous, then delta G should be negative. So the delta G should be negative. That is the thing. If process has to be spontaneous, then delta S has to be positive, delta G should be negative. This is the criteria for spontaneity of a reaction. Delta G of the system should be negative, then the reaction is spontaneous in nature. Clear it is? So remember, delta G should be negative. So we'll move on to the next one. So according to that equation, according to Gibbs-Helmond's equation, so we can check here, delta G at constant temperature and pressure is equals to delta H minus T delta S. So we have studied that delta G should be negative for a spontaneous reaction. Under what all conditions delta G becomes negative, we are discussing. Under what all conditions delta G becomes negative, we are discussing. Clear it is? Now, so if delta H is negative, so we have this reaction here. So if delta H is negative, then this part will be minus of T delta S. If delta S is positive, then if delta S is positive, minus into plus, then it becomes minus over there. So check if delta H is negative, that's how we will be analyzing. So already in the formula we have minus, and for delta S, temperature won't be negative. So delta S is positive. So minus into plus is minus. So delta H is negative and this part also becomes negative. So we can add up this one. Then delta G becomes negative. Clear it is? If delta G is negative, the reaction is spontaneous in nature. So we can mention that one as a spontaneous. So it is spontaneous in nature. Suppose if at all, if delta H is positive, let us think that delta H is positive. So we have delta H as positive and delta S is positive as it is. But this part is negative. When this part becomes negative, delta H is positive, minus into plus, it becomes minus. If our delta G has to be negative, then this should be greater. Then T delta S, if it is greater than delta H, then delta G becomes negative. If delta G is negative, then the reaction is spontaneous. I hope it is clear. So the conditions we are discussing, if delta H is positive, that is nothing but endothermic reaction. So if delta S is positive, that is spontaneous reaction. So we have two terms, one is delta H, another term is T delta S. So here now to make it a delta G negative, so this is negative and this is positive. So that is negative and that is positive. So if this is positive, when you consider this one, so that is already what we have used. Already we have seen this is negative and this is positive. That is nothing but the favorable condition. It is the favorable condition. On. So we have a favorable condition. This is negative and this is positive. It indicates that that is the favorable condition for delta G should to be negative. So if this is positive and this is positive, this is favorable condition. This one is not favorable. Clear? So we have two parts to decide delta G to be negative. One is delta H and another one is T delta S. So if delta H is positive, that means that it is not favorable. So but T delta S, where delta S is positive, it is positive, it is under favorable condition. Then so if at all, if it is minus, negative into positive, it becomes negative. Then if delta G has to be negative, means this T delta S should be greater. So negative at higher temperature. If temperature is higher, which makes this entire part little higher than delta H value. Magnitude is higher than delta H value. Then delta G becomes negative. Clear? So negative at higher temperature and positive at lower temperature. If temperature is less, then the temperature is less, then this part becomes less. Then at the time delta G becomes positive, which is non-spontaneous. So if this is greater, temperature is higher, then this negative part becomes more and delta G becomes more, then the reaction is spontaneous. Clear? Now delta H is negative. This is under favorable condition. Delta S is negative. That means that it is not under favorable condition. So clear? So both are favorable when it is both are favorable, when delta H is negative and delta S is positive. So at the time always delta G will be negative and it is spontaneous. So now delta H is favorable, that is negative value it is showing. Delta S is not favorable, it is showing negative value. So when you consider delta H and delta S, when you consider delta H and delta S, just a minute. When you consider delta H and delta S, so delta H is negative and delta S is positive. Delta S is also negative. So when negative and negative, so here if you consider negative, then the whole will become positive and this is not there. This is not there. So delta H becomes negative. So now delta G to be positive, delta G to be negative, delta H value should be higher or temperature value should be lower. Clear? For a reaction, you can't change delta H value. It is fixed. Enthalpy of the reaction is fixed. Clear? You can't change. But if the reaction is taking place at a lower temperature, then this entire part, this is the positive part. So entire part of this one will become less. At the time, if delta H is negative, then delta G becomes negative. Clear? Delta H is negative and delta S is also negative. So delta S is negative. When you consider delta S is negative, when you consider delta S is negative, so it becomes delta S becomes negative. Then negative into negative, this whole term becomes positive. If this part is more, if this part is greater in magnitude than delta H, then delta G becomes positive. If delta H is more, then delta G becomes negative. So you can't change for any reaction delta H value, you can't change, delta S value you can't change. But temperature, if suppose in a lower temperature, if the same reaction is taking place at lower temperature, then this part becomes lesser in magnitude than delta H value. At that time, delta G becomes negative. So we can say that delta G is negative at lower temperature and positive at higher temperature. If it is negative at lower temperature, then it is spontaneous. If it is positive, then it is non-spontaneous. Clear? Next one. So delta H is positive and delta S is negative. Delta H if it is positive. Delta H if it is positive, like that only. Delta S is negative. So negative into negative. So we can write it here. I'll write it here, negative. So this is not there. This is not clear. So delta S is also negative, in the formula also negative, and delta H is positive. Minus into minus plus. So this part is plus as well as this part is plus. It doesn't matter either lower temperature, higher temperature. Delta H will be always positive. If delta H is always positive, then it is non-spontaneous process. Then the process is non-spontaneous in nature. Clear it is? Followed. So these are not favorable or unfavorable condition. Delta H positive and delta S negative is unfavorable condition from both the sides. So here it is favorable condition. Both are under favorable condition. So always the reaction will be spontaneous. If suppose the temperature changes, or temperature variation is possible, then the reaction may become spontaneous or it may become non-spontaneous also. So these are the few conditions where delta G will become negative. Clear it is? So we'll move on to the next part. So that is Gibbs energy change and non-mechanical work. So one of the important limitation for second law was we couldn't able to find the useful work from that. Or first law of thermodynamics also same thing. So we say that heat is being utilized or energy is being utilized in the process, and that amount of energy we are not able to calculate how much amount of energy is utilized for the work. First law says that some amount of work is done, and in that some amount of work, how much amount of useful work we have done, it is not going to show us, or it is not going to tell us. Clear it is? So first law tells that some amount of energy is being converted as work, but in that work, how much amount of useful work is done, that it is not going to show. Now we are discussing about that work done. So the work done is, that useful work done is called as mechanical, non-mechanical work. Clear? Non-mechanical work. So whatever the work done, mechanical work is nothing but expansion. Gas is just expanding. But from that expansion of gas, how much amount of useful work we have done, that we are not going to calculate, that we are not going to get from first law. So now with the help of Gibbs free energy, we are calculating how much amount of work is done. Clear? So the relationship with the non-PV work, it is also called as non-PV work. So first law of thermodynamics, according to first law of thermodynamics, delta U is equals to Q plus W, where W includes pressure volume work, and it is also called as non-PV work. We also we can also write that one as minus P delta V. We used to write. So W is equals to minus P delta V. So when we are writing work here, it includes minus P delta V, along with that some useful work is done, and that useful work is called as non-expansion work or non-mechanical work. Clear it is? So whatever the work we have written, it is P delta V. This work part is mechanical work or expansion work. So work, remember, so now we have distinguished work. In that work, it contains some expansion work and some non-expansion work. Expansion work is also called as mechanical work. Non-expansion work is also called as non-mechanical work. And this non-expansion work or non-mechanical work is also called as useful work. Clear? It is also been called as a useful work. So now we shall see. So what are this equation? Delta U is equals to Q minus P delta V. W can be written as expansion work plus non-expansion work. Expansion work can be written as minus P delta V, and non-expansion work W non-expansion we have mentioned. We'll just rearrange the equation. So if you just rearrange the equation, Q we have shifted, Q we have kept there itself, we have shifted this part to this side. So delta U is delta U plus P delta V minus W non-expansion. So delta U plus P delta V can be written as delta H. We have written in our earlier cases we have discussed. So delta U is equals to delta U plus P delta V can be written as delta H. Clear? Now, so now this Q we are going to substitute. So what is that Q? Delta S is equals to Q by T, or Q can be replaced by T delta S. So we are going to replace that one. T delta S is equals to delta H minus work of non-expansion. So delta H you shift that one that side. Then it becomes delta H minus T delta S is equals to work of non-expansion. Delta H minus T delta S is equals to work of non-expansion, and delta H minus T delta S can be written as delta G. Delta H minus Gibbs Helmonds equation, delta G is equals to delta H minus T delta S. So delta H minus T delta S, we have replaced that one by delta G. We have replaced that one by delta G here. So this one we have replaced by delta G and work expansion as it is. Now we are going to take a negative sign on both the sides. We have taken negative sign on both the sides. Clear? So what does it indicate? This negative sign indicates negative delta G or decrease in Gibbs energy, indicates that it is the reaction is spontaneous. Clear? If the reaction is spontaneous, then W is also negative. Minus W indicates that work is done by the system. Work is done by the system. So we can conclude that decrease in Gibbs energy, that is negative delta G, we have written as decrease in Gibbs energy. Decrease in Gibbs energy is equals to non-expansion work done by the system. That is expansion. So non-expansion work means useful work is done by the system. Clear? So useful work done is by the system can be calculated by using a minus delta G value. If you get a delta G value or minus delta G value, we can say that that is equals to amount of work done by the amount of useful work done by the system. So non-expansion work can be put to useful purpose, and it is also called useful work or free energy of the system. Clear? It is useful work done. So by using Gibbs free energy, we have calculated. We have removed surrounding and we have calculated how much useful work is done by the system. Clear? Next, third law of thermodynamics. By this we can define third law of thermodynamics. At absolute zero, the entropy of a perfectly crystalline substance is zero. Absolute zero indicates the temperature. Absolute zero, the temperature, it indicates if at all, if absolute temperature is concerned, it is 0 Kelvin or 273 degrees Celsius. At absolute zero, the entropy of an perfect crystalline substance, if the substance is perfectly crystalline, then the entropy of that substance is zero. Perfectly crystalline is nothing but solid substance. So the substance is solid, where if the substance is solid, the particles are highly orderly arranged. There is no randomness, so they are orderly arranged. So because of which the entropy becomes 0. Clear it is. At absolute 0, the entropy of a perfectly crystalline substance is 0. This is what the third law of thermodynamics. So all those equations and the formulas which we have discussed is very, very important. Next, last part, Gibbs free energy change. Gibbs energy change and equilibrium. So we have a formula. The formula is direct here. So in NCRT, it is a direct formula given. So we have one or two graphs over. Therefore, are competitive. We shall discuss that one, how the formula and what is the graph and all we can discuss. But when we are discussing the theory part, only this much. Delta G is equals to delta G naught plus RT ln Q. What is this delta G naught? Delta G naught is nothing but standard Gibbs energy change. So delta G naught, whenever we write naught, naught indicates, in thermodynamics we have studied, whenever we write naught indicates, that is thermochemistry you have studied. So in thermochemistry you have studied that whenever we write naught here, so the naught indicates it is a standard Gibbs energy change. So the definition of that one is, so the Gibbs energy change for a process in which the reactant in their standard state, the reactant should be in their standard state, are converted into products in their standard state. So in a reaction, the reactant is also standard state and the reactant is being converted as product and the products are also in the standard state. Then the Gibbs energy change for that reaction is called as standard Gibbs free energy change. So what do you mean by standard state? Standard state is nothing but the substance in its elementary form or in the however it is, either it may be monoatomic, it may be diatomic, however they are present, it should be in the standard form, that is more stable form. Suppose when you consider hydrogen or oxygen or nitrogen, if you consider, so H2, N2, O2, diatomic form, they are stable. And in the gaseous form, they are stable. That physical state matters. So in which of the physical states it is stable, so that indicates the stable state or standard state of the substance. Clear? So if the reaction in which the reactant and products are in the stable state or are in the standard state, then the Gibbs free energy for that reaction is called as standard Gibbs free energy. And this Q we have written ln Q. Ln is nothing but natural logarithm. Already you have studied in equilibrium. It is natural logarithm. So that is nothing but log to the base E. Q is nothing but reaction quotient. That is, a reaction is taking place and the reaction has not attained equilibrium. Clear? It is before equilibrium. So before equilibrium, the reaction has not attained equilibrium. If you take the ratio of concentration of the product divided by concentration of the reactant, then it is called reaction quotient. Once when the reaction is attained equilibrium, then we are not using Q, we are using the term as K, because the concentration of reactant and the concentration of product remains same. I mean remains same in the sense how much it was, the constant value we are going to get. So that constant we are calling as equilibrium constant and that is being indicated by KEQ. Clear it is? So Q is a reaction quotient. It indicates the ratio of concentration of product divided by concentration of reactant. It is before attaining equilibrium. The reaction before attaining equilibrium. Now the reaction is at equilibrium. So at equilibrium we have a condition delta G is equals to 0 and Q is equals to KUQ. That is nothing but equilibrium constant. KUQ indicates equilibrium constant because this value becomes same. Concentration of product is constant and the concentration of reactant also remains constant. So because of which this ratio becomes constant. So we have taken a term as equilibrium constant. Clear? Now, so now the process, now the formula reduced to. So G is delta G 0. 0 is equals to delta G naught plus RT ln Q. Ln can be written as. So if you shift delta G naught is equals to minus RT ln Q. Ln Q is being replaced by K equilibrium or equilibrium constant. So to calculate, you can't calculate or you cannot use this formula for calculation, because log to the base e or natural logarithm. So that table, rather than using that table, we are using log to the base 10 table. That is what we are using for calculation. So that's why natural logarithm will be, or log to the base e is being converted as log to the base 10 by multiplying by 2.303. So we have multiplied the equation by 2.303, or the term by 2.303. 2.303 RT log to the base 10 K equilibrium. So this is a very important formula. Mark this formula, and it is important for competitive. So this formula is important for competitive. Mark it down. So it is very, very important. Important. Clear? So by this we have completed our thermodynamics chapter. So we have a few problems to discuss. In our next class we'll discuss about the problems, and from next to next class we are going to discuss our competitive part also. So very important chapter. Usually 3 problems will be expected in CET level at least, and NEET at least 1 or 2 questions. Compulsory 1 question at least will be there from this. So numericals, more importance is there for this numericals in this chapter. So that's why JE also, for JE also, this is a very important physical topic. So make sure that you complete this chapter with the formulas, practicing all those formulas and all. So in our next further classes, we'll discuss about the tricks and hints how to solve these problems. Thank you.